Hi everybody, welcome to your Unit 1 Section 2 notes. This will be part 1 of 2 videos that you will watch today in order to get your notes done in your Section 2 green sheet. So if you don't already, please find your green sheet. So you can pause the video, go find it, and come back. If you can't find your green sheet, what you need to do is go to the class resources page on Canvas in your applied chemistry class, and you can pull up the Section 2 green sheets. We have them there, so download that and then you can take the notes as we go along. But you should be taking these home with you every time you go home. So you should have this ready. So you should be looking for Section 2 up at the top right corner, and it should say States of Matter here. Alright, and we are going to get started. The first state of matter we're going to talk about is the gas state. So you can write in the blank right here, gas state. Right, these particles are very spread out and they move around a lot. They move very fast, very quickly. Right, they're constantly bouncing off the walls of the container, whatever container they might be in. They're constantly bouncing off each other. You can get a good look at what a slowed down, very zoomed in view of what some gas particles will look like at the bottom of the video. Alright, so gases, they do not have a definite shape. Right, so we will write on our green sheet here, they do not have a definite shape, right, and they do not have a definite volume. No matter the size of the container, right, a gas will take the shape and the volume, or the amount of space that it takes up. You might think about somebody walks into class with a very strong scent, like maybe they put on too much cologne in the morning. Right, and you can smell that cologne from the other side of the room. These gases are going to spread out and take up the size of the container. Right, that's part of why being outside right now during the coronavirus pandemic might be a wise thing to do, because when you're outside, the volume of the container, right, is the entire atmosphere instead of an enclosed room. Right, so we're spreading, right, less gases back and forth with each other. Right, you still want to keep that 6 feet though. Some examples would be oxygen, nitrogen, methane, CO2. You can write these in. I'm going to write the abbreviations, right, our symbols. Methane would be CH4, and then CO2 was carbon dioxide. No, they do not. Alright, so for your drawing, right, I know you can't draw a moving image, so we're going to draw circles or dots with arrows looking like they're bouncing everywhere. Alrighty. Moving on, our next state of matter is going to be the liquid state. So we can write that in, liquid state. These particles are close, but they freely move over one another. You can see in the diagram below, they'll stay close to each other, but they are always moving around one another. Kind of like a very peaceful mosh pit, right? Everybody's kind of moving back and forth, swaying back and forth. But they're also falling over top of each other and going underneath of each other and just moving all around. Liquid particles do not have a definite shape, but they do have a definite volume. You might think of if you pour yourself a glass of water, right? The water is not going to fill up the entire cup until you put enough water in it, but no matter how much water you put in there, it's going to fill up at the bottom first. And it's going to fill up the whole bottom. That's because the water, the liquid, is taking the shape of the container, right, but is not expanding its volume as it goes in there. Some examples of liquids would be water, gasoline, or vegetable oil. And you can write these in here on your notes. Now, for the sake of time, I'm going to stop writing the notes with you, but I will move the page along so that you can see where you should be. All right. So we should have both the gas state and the liquid state done. For our drawing, I will do the drawings with you, right? Because we can't do the nice moving diagrams like we have there. Let's draw a bunch of circles, but make sure that they are just covering the bottom of the container, right, or the bottom of our box there. All right, and you can show that they are moving if you want to draw a couple small arrows just to show that they are moving. Alrighty. Our last state of matter we're going to talk about is the solid state of matter. Right, these particles are very well organized and tightly packed, right? But they're not stationary. They're not standing still. They're vibrating, constantly vibrating, but they do stay in the same place. You can see in our diagram below, right? They're just standing there vibrating. So even that desk that you have your computer sitting on, right, or the pencil or pen that you're writing with, right, the atoms in that object are constantly vibrating, even though you don't feel that. Solids do have a definite shape and they do have a definite volume. That's why if you place something like a set of dice in a cup, those dice are not going to spread out and take up the whole bottom of the cup. They're going to keep their same shape. Right? If I throw my pen across the room, right, it's going to still have the same shape. If I move it to a different type of container, the shape of my pen's not going to change, and the amount of space that my pen is taking up is not going to change either. Some examples of solids would be ice, steel, and rock. I'm sure you can think of hundreds or thousands of other examples of solids. All right, for your picture, I'll make sure you can see that here. All right, I might draw a nice cube of circles. So that shows that my atoms are tightly packed together, right? But they're still holding their own shape and holding their own volume. They're not spreading out and they're not filling the bottom. They're staying together. And if you want to write somewhere here that they are vibrating, that might be a good idea. Alrighty. The last thing we're going to talk about is the measure of average kinetic energy of molecules and atoms. Right? So we talked before, and in your chem words, right, you should be familiar now with the definition of temperature. So the definition of temperature is not how hot or cold something is, right, but it's a measure of the average kinetic energy of the molecules or atoms in that substance. So something that is very hot has atoms that are moving very fast, while things that are very cold have atoms that are moving slower. Right? That might be why gases, right, are bouncing off the wall, but solids, right, are just vibrating in place because the gases have more kinetic energy than the solids. Right? If you touch something hot, right, what's actually happening is the very fast-moving atoms and molecules in that hot substance are colliding with the very slow molecules and atoms in your finger or your hand and speeding them up. And that collision is when you feel that pain. Right? And the reason that we don't say that the definition for temperature is how hot or cold something is because that's relative. Right? A stovetop might be hot to us, right? We don't want to touch it with our hand, we'll hurt ourselves. But when you compare that temperature to the temperature of a star, right, something like our sun, it is relatively cold. But it will be silly for us to say that our stove is cold when we know it is hot to us. Right? So that's why we're going to stick with the definition for temperature as the measure of average kinetic energy of molecules and atoms. Alright, so sorry for that little glitch there in the video. I skipped something. I don't want you to miss out on this. So we're going to talk about some phase transitions, right? Or going from, right, one state of matter to another. So if you can turn the page, You should see a diagram that looks like this. And all you need to do is fill in, write in the name of the phase transition as we go along. Right? Some of these are going to seem very familiar to you, and other of these are going to be new. You are going to be required to know all 6 of these phase changes. All right, so without further ado, let's get started. When we go from a solid to a liquid, we call that melting. Right, so you're going to write in right above the arrow, right underneath the arrow, melting. All right, I'm not going to write in the rest with you. Right, you can do that yourself as you follow along. All right, so as we go from solid to liquid, we are melting. As we go from liquid to gas, we call this boiling or evaporation. Both would be considered correct answers. Alrighty, now for both of those, as we're going from solid to liquid and liquid to gas, right, we are getting warmer. And by that I mean the particles inside our solid, right, are moving faster and faster and faster until they become a liquid. And as they become a gas, they're moving faster and faster. So we are increasing in energy as we go from solid to liquid and liquid to gas. So melting and boiling / evaporation is an increase in energy. Now, believe it or not, you can even go from a solid right to a gas. If you've ever seen dry ice before, I know we recently watched a video on what is dry ice. Right? It's undergoing a process called sublimation. Right? Not transvaporation or whatever that guy came up with. Transhydroevaporation. It's sublimation. Right? So you should be writing that up top here at the top arrow. So in a sublimation, we're going straight from solid to a gas, just like our dry ice. All right. When we go from a gas to a liquid, we call that condensation. Right? This might happen when you have a water bottle outside on a hot summer day and it looks like it's sweating. Or maybe you take a hot shower and some of the steam from that shower condensates on the mirror. And that's why your mirror has those droplets all over it. Alrighty. When we go from a liquid to a solid, we call that freezing. I'm sure that's not new to you. Both condensation and freezing are a decrease in energy. So we are losing energy. Our atoms and molecules are slowing down as we go through condensation or freezing. And believe it or not, we can go from a gas to a solid, and that would be a deposition. A very good example of this might be freezer burn that you see from like ice cream or meat that you put in the freezer. So as you open and close your freezer door, right, you're letting moisture from the air in your room get trapped inside there. And as that water vapor or that gaseous water in the air is trapped inside the fridge, right, it goes straight from a gas to a solid, and that's why that ice that comes from the freezer burn looks different from the ice that you had in your ice cube tray, because the ice in your ice cube tray is just going from a liquid to a solid. Alright, so that is the end of the PowerPoint, but don't close the video just yet. I want to show you what you're going to be tasked with doing. So if you could turn to page 4 in the section 2 of your green sheet, you should see a table with a Venn diagram, and I'm going to need for you to complete that before you watch the next video. Alright, so we did do some examples for you on here, so you can follow along. As we're boiling, we're going from a liquid to a gas, and we are gaining energy. So you might try to think, right, are the atoms speeding up or are they slowing down? If they're speeding up, we are gaining energy. If the atoms are slowing down, we are losing energy. So with condensation, we're going from a gas to a liquid, and we are losing energy. Sorry, I gotta be quick. We're coming up on that 15-minute mark and my video shuts off. Instead of rewriting every phrase inside the Venn diagram, it might be easier for you if you just write the numbers in and then cross off as you go. So number 1 is particles in an organized pattern, and you would just write a number 1 in there. So best of luck. Make sure you finish this before you start watching the Notes Part 2 video. Alright, I'll see you later.